Hello, and welcome to our simulation part of our supercritical fluid extraction lesson. Right here we have a simple simulation of supercritical fluid extraction of coffee beans. We will be extracting caffeine from coffee beans, and the caffeine is going to have a 1% weight against the beans. We're going to be feeding a water co-solvent and mixing it together in order to have an even mixture to extract the caffeine from in the chamber. And from this chamber, we're going to be sending it to an extractor that's going to allow us to recycle the CO2 back into the compressor for reuse and separate the extractor in order to send it to a centrifuge so that caffeine and water can be separated from the beans. One thing I would like to note is that before you start the simulation, you set up your properties and your components. And so I define my components as such. The reason why beans are non-conventional is because Aspen is not going to accept an input of coffee beans because it doesn't have thermodynamic properties from coffee beans, which you actually have to define on your own. I did so right here. I defined the density and the heat capacity of the beans in order for me to be able to perform thermodynamic calculations to separate the caffeine from the beans using water and CO2. Also, one of the things that you need to take into account is the non-conventional properties. There are enthalpy and density, which are going to be used in our feed so that we can define some of the properties of the beans that are going to be used by Aspen for calculations. So another thing is the methods that are being used. Peng-Robinson method is used because it is an industry standard, and so it is the equation of state of choice. UNIFAC and UNIQUAC is used to be able to perform thermodynamic calculations for the beans against the caffeine and the water and the CO2. Without these, Aspen cannot recognize some of the properties of the caffeine and the beans, and so it will not perform the calculations necessary if these aren't inputted in. So back to the simulation. I'm just going to show you how some of this has been introduced. So right here I define my non-conventional solid, which is the beans, at normal conditions. And so this was the general analysis that you saw in the previous section, and we were just defining that as 100% beans. It doesn't contain any other components. And then we define the particle size distribution to be between 0.9 and 1.1 centimeters as a way of simplifying the process. And that way Aspen can define what size these coffee beans are going to be and whether they're going to be separated successfully by the centrifuge. And right here you have to also define your mixed stream, which would be your caffeine in this case, and it is at normal conditions. And so one of the things that you notice that you probably have not seen before is these manipulators. What these manipulators do is they transform two different parts of the flow sheet. What I did is I created two parts. One of them was bean and one of them was global. The global is going to accept all the conventional and mixed classes of streams, and the bean is going to accept all the streams that have to do with non-conventional solids like our coffee beans. And so what these guys do is they transform the CO2 feed, which is conventional, into another class, which is a mixed non-conventional solid feed. And so the blocks are going to require all the streams to be of the same class in order for it to perform all the calculations necessary. And so these guys are very vital to performing the simulation successfully. And so you'll notice that I have another one right here, and this one converts it from mixed back to conventional so that the compressor can use it to perform calculations. And so when the simulation is run, we notice that it is a perfect separation from the feed over to the out feed. And so that shows that it has been a successful separation, and that it is definitely a viable alternative as a separation technique in the future, which is greener, and it will produce less emissions, and it will help us save the environment. Thank you for listening, and I hope you learned something today, and hopefully you make your own simulations as well, and hopefully I have helped out with some Aspen tools for you to use in the future. Thank you.